Welcome, this is lecture number 44. In this lecture, we are going to talk about small signal and large signal model based nonlinear control. So, in this lecture, first we will talk about summarize small signal and large signal models. Then I will discuss about gain scheduling method using linear parameter varying model. Then I will also talk about large signal control and stability using Lyapunov function, and then followed by exact linearization and nonlinear control using large signal models. So, if we recall that our ideal boost converter and state space model, so an ideal boost converter, the switching converter, where we are we can write the state space form, and here we are considering the state space model to be inductor current is one of the state, that means inductor current is one of the state, inductor current, and the other state we are taking output voltage, but actually it is the capacitor voltage. We should take the state variable since it is an ideal converter. So, the capacitor voltage and the output voltage are same. Then we can write x dot equal to AQX plus BQV in, where Q is the gate signal, and we know that Q equal to 1 when S is on, right, the main switch S is on, and it is 0 when S is off. We know that. Okay. So, now for Q equal to 1, our A1 matrix will be 0 0 0 minus 1 by RC, and when Q equal to 0, then we will get A0, which is this matrix. Okay. And this is standard thing we have already discussed multiple times. Now, for a boost converter in continuous conduction mode, the input voltage is always connected. So, B matrix are common, they are all identical for two different configurations, because the input voltage is common. It was the it was the other case for the buck converter, where input voltage was connected and disconnected. So, we got different B matrices for switch on and switch off, whereas A matrix was common for the ideal buck converter, but it is just the opposite for a boost converter. And since we are talking about the ideal boost converter, the capacitors are also common, because what I have not written is the V0 is equal to CQ into X, where CQ, that means Q equal to 1, C1, C0. For an ideal boost converter they are same, but for practical boost converter, if we incorporate the ESR 0, that means the ESR of the capacitor, then there will be discontinuity in the output voltage ripple, and that will make two different C1 and C0 output matrices different due to the ESR. But here we are talking about ideal converter, but we can do it for practical also, no problem. Next, what we did? Next, we obtain the average small signal model, and we have discussed multiple times that traditional, if we operate in pulse width modulation, we can apply traditional averaging technique, where this average quantity is nothing but it is the, if we take any variable, its average over a complete switching cycle 0 to t, right, and that we are denoting as x bar. Okay. So, now this x bar dot, the average dynamics, we will soon find, and we have already discussed that it is basically a vector, because we are taking two states. So, it will be 2 cross 1. Similarly, this vector function is also 2 cross 1, right. So, it is a vector, whereas the output voltage is a scalar, because it is just the output voltage, and this is a scalar quantity that we have discussed. So, what is this F average? This is a standard averaging technique, D into A1 plus 1 minus D into A0, where A1 is the system matrix when the switch is on, and A0 is the system matrix when the switch is off, and B1 and B2 are the system matrices, input matrices when the switch was on and off respectively. So, by that way we can obtain this average model, and we can also obtain this average model and for the output voltage, since our output voltage is constant, and for this ideal case it will be simply x2 bar, because we have taken x2 bar. X2 is the instantaneous capacitor voltage, for the ideal case it is the output voltage. So, you have to take bar, means because we are talking about the average model. Okay. Now, if we see this f average, that means this vector function as well as this output scalar function, they are basically smooth function because we have replaced actual gate signal q by d. You see, with the original switch model, the q was discontinuous because it is a switching, either it is on or off. But when we take the average, then this discontinuous function is replaced by a continuous function. And in that case, q can take the value, discrete value 0 and 1, whereas the d belongs to the open interval of 0 to 1 because we are not considering the extreme cases, that means d equal to 0 and d equal to 1 we can take, then it will not behave like a DC-DC converter, because if we operate either fully on or fully off state, then we will not get the desired output voltage. Okay? So, we need a switching operation. As a result, our duty ratio should be in between 0 to 1, it should not be equal to 1 or 0, equal to 0. But this can happen when we go for switching surface based control, where we allow the duty ratio to saturate, because in that case if we allow the duty ratio to saturate, we can obtain something called time optimal or the fastest transient response, that we will be discussing in the next week. But in this lecture, we want to limit the duty ratio between 0 to 1, and that is why this function, since d is a continuous function, so both the vector and scalar functions are continuous, and we can take the partial derivative of this as well as this, as many times as we want, and that is why, and they will be continuous, that means there will be different derivative will exist, for various higher order derivative will exist. So, it satisfies the Lipschitz continuity. So, if satisfy the Lipschitz continuity, and in fact it satisfies that you can take differentiation at any number of derivative, but the derivative will exist because there is no discontinuity. So, this is a perfect example that this nonlinearity, for this nonlinearity we can apply Taylor series approximation. If we have a function with discontinuous function, then we cannot apply Taylor series. So, it is a continuously differentiable function. So, next, this average quantity we can write in Taylor series, because we have an average dynamics that can be replaced by approximately this function at certain point. So, here I am writing, when I am writing this any x s s, this represents actually x at steady state, that means these are the steady state quantity. Steady state quantity. Okay. So, that means when we are talking about steady state, means we are trying to obtain the approximate Taylor series approximation around a steady state point. But you can also approximate using the Taylor series for any arbitrary point, which need not to be steady state, which need not to be operating point, but whether you are going to get the perturbed linear model or not, that we are going to discuss. But the Taylor series approximation can be applied for any arbitrary point. It need not to be an operating point, or it need not to be a steady state. But in this case, we are considering steady state because we want to obtain linear model under around a steady state operating point. So, what is the higher order term? If we write down the higher order term means it consists of dou 2 f dou x2, then it consists of dou 2 f dou d2 and another higher order term, and that we are writing, clubbing together to write higher order term. So, now if I write all the instantaneous average quantity, that means x to be its steady state value plus perturbation. So, sometime we write perturbation to be tilde, sometime we write hat. So, you can assume that these are perturbed quantity. So, when you write any state, similarly we can write duty ratio to be capital D and then D perturbation. Similarly, we can write input voltage average V in plus small v in perturbation and so on, right. So, you can write everything. Now, left side, once you take x average dot, that means you can write xx dot plus x tilde dot. Interestingly, since it is a steady state point, this part will be 0, this part will be 0. So, it will become x tilde dot, right. So, write this, since this part is 0. Similarly, if you solve, that means if you solve this equation, that means here if I simply take steady state dot will be equal to f average x steady state. So, I am writing x steady state comma d capital D comma capital V. So, this term must be 0 because this is the operating point steady state. So, from this we can solve for xx in terms of duty ratio, input voltage and so on. So, this quantity will also be 0 at steady state, that we have discussed. So, this is 0. So, we will have this term, we will have this term, but higher term we are neglecting because we are trying to obtain linear model, and we already have discussed earlier when we carried out circuit averaging technique, state space averaging technique, where we ignore the product of perturbation, that also ignored, right. Product of x1 dash or tilde, you can say, these terms we have neglected. That means higher order terms we have neglected earlier, so they are not coming to picture. So, the approximate model here is simply this model, where we can write a into x tilde plus b into d tilde, where a is nothing but this particular function and b is nothing but our this particular operation. Okay. So, we can obtain now linear parameter. Why we call linear parameter varying model? First of all, this represents a linear model, part of linear model that we have discussed, because we will see that because we have linearized around the steady state point and there is no product of perturbation term. So, it is a part of quantity or the deviation variable. That means we have obtained x dot, and this was our A matrix, this was our B matrix, and this is a disturbance matrix because supply disturbance. Now, you will see in the A matrix, if you take this A matrix has information of the duty ratio, A matrix has the information of load resistance, and LC are the system parameter which are generally fixed during the design process. That means, we generally do not vary inductor or capacitor, but in a practical circuit there can be variation of inductance and capacitance, because the inductance is nothing but it is coming from the magnetic BH curve. So, this inductance may not behave like a constant value if we try to operate towards the saturation or the nonlinear region of the magnetic curve. But if we operate them in the linear region, then inductor will be more or less constant and the variation is not very significant. Same thing is for the capacitor. So, we are assuming the L and C variations are insignificant, but and those are fixed at the design stage. So, they are not going to vary during the run time, except for small variation in inductance that I have discussed. But what here going to vary? Suppose if there is a change in input voltage can change, load resistance can change. So, this quantity can change, right, because the load resistance is the external quantity, which actually, because this load, because you are supplying, the boost converter is supplying to a load, it may be a processor load, or sorry, it can be, if we talk about electric vehicle, auxiliary power. So, there are many applications wherein boost converter. So, the load can vary. When the load varies, supply can vary, then the duty ratio will vary at steady state resistance. So, A matrix depends on the parameter. That is why this model is called linear parameter varying model. Linear parameter varying model, where the A matrix consists of parameter and those parameters will be decided, and you will see this A matrix will vary, it varies with varying R or V in, which is the duty ratio. Now, if we recap, so once you have this linear model, that means this is our linear model, this particular circuit, we can obtain various transfer functions. So, we can design a closed loop control of this boost converter either by voltage mode control that we have discussed. We can design using current mode control, and we have also learned that current mode control has an alternative state feedback realization. So, state feedback realization, right, that also we have learned. So, state feedback realization. So, we can implement different type of control using this part of or linear parameter model. For example, if we recall our boost converter under voltage mode control, we have used a PID controller where the control to output transfer function of the boost converter consists of one right up plane 0 and of course, there are two stable complex conjugate pole in general, and we have already discussed that what are these omega 0, the natural frequency, then what is the RHP 0, right up plane 0 frequency, then the Q factor, and this is also a function of characteristic impedance. So, all these things we have discussed I think in lecture number 36, where we discuss about design of boost converter using voltage mode control. And we have also discussed in that lecture that we can use a practical PID controller, for example, where the structure of the practical PID controller is Kp, that proportional term, this is my P control, this is my I control, and this is my band limited derivative. So, it is a band limited derivative, this is my derivative control, okay, where we have a derivative filter. So, this is a derivative filter. Now, in summary, we have a controller which is a practical PID controller, that structure looks like this, and we can set this PID controller parameter because we have discussed the analytical method of design by means of stable pole 0 cancellation, and we have cancelled the stable pole by means of the zeros of this PID controller. And if you do that, then but what we did for the right up plane 0 in we cannot cancel because unstable pole 0 cancellation is not allowed, otherwise it will make the system internally unstable. So, we placed a right up plane 0, we placed the controller one of the pole in coincidence in coincidence with the RHP 0. That means, we want to coincide the controller pole with the RHP 0, and that is why we have chosen. And this part, and after that we have analyzed by computing the gain crossover frequency, and we saw this the bandwidth, that means which is the gain crossover frequency that we have discussed. We have discussed the gain crossover frequency. It is in radian per second, radian per second. So, this gain crossover frequency we found for a voltage mode control, it should be less than equal to what? Minimum of RHP 0 by 5, comma, switching frequency by 10, all are in radian per second. So, it should be the maximum that we have discussed. Okay. So, this once we select this omega c, and since our duty ratio is known and the modulator gain for voltage mode control, we are assuming that your controller that sawtooth waveform, that means sawtooth waveform is already decided, and if this is our Vm, then we know that Fm equal to 1 by Vm, that we have already discussed. So, you can select the integral gain and the other gain parameter are already decided. Now, since you see the controller gain K1, K2, Ki, tau d, K2. So, what was omega 0? So, for a boost converter we know omega 0 was 1 minus d square root of LC. That means, this quantity is duty ratio dependent. And what we learn about Q? we learn about Q is equal to, if you go back, Q equal to R into 1 minus D by ZC. Okay, that means our Q was, what was our Q? R 1 minus D by ZC, that is the characteristic impedance, and those things we have learned. That means we have learned this. So, this is also function, and we have also discussed RH0 is also function of. So, what was our RH0? It was R 1 minus D whole square by L, because if you go back, we can say R 1 minus D whole square by L. So, that means we have discussed. So, all these parameters of the controller depends on load resistance and duty ratio, and duty ratio is a function of input voltage. So, that means if we want to, so if we design by traditional way where we design this compensator or the PID controller or type 3 compensator at the very beginning stage, that means we use off the chip component and we select it and then we leave it. Then throughout the process, when there is a load variation, supply variation, we are not going to change in the traditional analog control. So, as a result, you have to design this controller based on the worst case. So, we have to design based on the worst case, and the worst case means it happens generally at highest, at highest duty ratio and highest load current. But your converter may not operate in this worst case condition all the time. In fact, most of the time it will operate in other operating point where because of this worst case design we lose the performance benefit. So, it will be very slow. So, one of the way is the gain scheduling technique. That means we need to update the controller parameter. So, there are two ways. We can still use a PID controller throughout, but this PID controller coefficient, that means if we take the coefficient of the PID controller of, or its coefficient I can say, so the coefficient should vary. That means this coefficient to be updated when R or V changes, and that means that is a kind of a scheduling, when to change, how to change. So, this gain scheduling has 4 steps. The step 1, we first compute a linear parameter varying model. In fact, we have it. In fact, we have this model which is A into x tilde plus B into d tilde plus E into V in tilde, and this is something like a function of load resistance and duty ratio. So, this linear parameter varying model which is arising due to this A matrix, we can obtain by Jacobian. So, in our case we do not need to obtain the linearization matrix all the time, because we know the linearized model, but what we need to obtain? We need to obtain the coefficient or basically A matrix, and we need to obtain control to output transfer function for various load resistance and the duty ratio or input voltage. So, we need to get a family of equilibrium point. That means what is, so that require what is my range of load, or in other word if I talk in terms of load current. So, this require the information of my load current. What is my load current? So, let us say it varies from 100 milliampere to let us say 5 ampere. Similarly, if your duty ratio varies from let us say 0.2 to let us say 0.6. So, that means within this load range and duty ratio we need to compute this GVD for certain range, because we need to take some combination. That means we need to take certain combination of D0. For example, I can take load current to be 1 ampere and duty ratio to be 0.3, like that. So, this combination, we can take this combination, and we have to design the controller. That means you get the PID controller parameters. That means we need to obtain the different operating point. So, we will get multiple operating point, because how many current you will take and how many duty ratio you will take. So, you may get infinite number of set, but we are not interested in so many operating point. So, you have to choose some operating point where we have more interest, and particularly we need to consider the highest and lowest load current condition, because if we unnecessarily use very this highest load current, you have a real restriction in terms of right of plane 0, but the lowest load current you have real restriction in terms of Q peaking, because at light load your damping can be really poor, and so you have to take special care in the either PID controller or type 3 compensator, whatever it is. So, step 2, as I said, we need to design PID controller for various operating point. That means we can say that operating point may be XX1, then we can say operating point XX2, and so on. Maybe we can have, let us say, 10 such operating point, and for each operating point I can say I have assigned some PID controller gain. That means I can write here KP1, KI1, KD1, tau D1. So, by that way we can write KP 10, KI 10, KD 10 and tau D 10. So, these parameters once we obtain offline, we can simply plug in to lookup table. And we write lookup table, right. So, here lookup table is my x's, and here I can say KP, KI, KD, tau D. So, for number 1 point you will get a set of controller, number 2 point you will get a set of controller, and these are stored in a lookup table. So, store using lookup table. Okay. So, should be multiple operating point we can compute, and then this may result in a family of PID controller gain. That means you will get multiple set of PID controller gain, and that will create a family of controller gain. Then what I will do, for each coefficient I can use a lookup table, the scheduling variable. That means, but the question is, how can we get the information of load current and input voltage? How can we get? So, one way we can do direct sensing. That means you sense I0 and Vin. Generally, this Vin sensing is not a difficult task, because if you go to commercial IC, we can keep that provision, that input voltage sensing. But the load current sensing is something is very difficult in fact. But if we take, let us say, LED driving application, a boost converter, let us say you have a boost converter, it has a supply V in and it is driving an LED load. Now, this is a dimmable LED, that means it is PWM dimming. That means the LED current which is going out, LED current, that will either high low, but it will change between its nominal value and zero value, nominal 0, and depending upon the number of strings this value can change. So, you know the value of the current, and if there are multiple string, we will know what are the different nominal current rating, and we are only controlling the switches of the dimming switches, right, of the boost converter. So, as a result, by changing these dimming switches, whenever we are changing, we are essentially getting the information of the nominal load current, and that can be used to tune the controller or get the parameters. So, this is another possibility. Similarly, if you go for battery charging, it is easy because battery charging anyway you are sensing current. If you are going for other application, let's say you are going for electric vehicle, where the boost converter, there can be multiple auxiliary power supply, or sometimes this boost converter is used to step up the DC-link voltage for the inverter, where this boost converter output current can be measured, because in high power application it may not be very difficult to sense current, where because the switching frequency is not very high. But if you are going for low voltage high current application, then this might be difficult, because sensing current in the high current path is really a tough, difficult job. But we can also use some kind of estimation algorithm, which may not require to sense the current, but then we can get the information and you can schedule it. And finally, once we set or we change the controller parameter using lookup table, then we can try to get the maximum benefit using this algorithm, and by that way we can improve the performance. So, your design will not be limited by the worst case scenario anymore. But all these are very effective when you go for a digital control, because this lookup table arrangement, the updating parameter, that makes sense when you implement a digital control, but this may be really difficult in analog control. So, whatever gain scheduling technique we are talking about nonlinear control, these are the motivating case to go for digital control for future. Okay. So, the gain scheduling summary, we have a controller where the parameters we have already discussed, and the integral gain can be obtained, and where all the parameters informations are given. So, we need to update the controller gain when the duty ratio and the load resistance or rather load current changes, and that we have discussed. So, this way we can get better response than fixed compensator based design. That means where you are fixing the compensator gain at the very beginning in analog control, where we do not have flexibility to change the controller value abruptly, because they are implemented in the off chip or outside using parasitic. That means actual I would say not parasitic, actual component, okay, where changing resistance outside component, capacitance, and all these values are really difficult. But once you plug into digital, where the coefficient is just a number, that can be updated by this method. So, this method can improve performance over the worst case design where the controller gains are fixed in analog control. So, this will because we are going to take the case study in the next week, I mean in the week 12, when we talk about analog control using fixed compensator worst case design, then we will talk about the design based on the gain scheduling, or basically updating the controller parameter, and then we will also consider some other nonlinear control to compare. Okay. So, the limitation, still the linear parameter varying model, they rely on the small signal model, because if we have a large perturbation, because of the validity of the model, if the perturbation of the reduce is large, then model is not valid. So, due to this validity of the model, we need to really slow down the controller. Even if we update the parameter, it is not sufficient, because the duty ratio perturbation is considered to be small. So, the performance limit is due to the model limit because of using small signal model, right. And we have also seen the state feedback approach can be a better alternative compared to traditional current mode control, as well as of course voltage mode control, because voltage mode control is not sufficient for a boost converter. And there we can use again this Taylor series model, and we can get the linear model and design based on state space. So, again the linear parameter varying model, state space model, where what we did here, we have implemented, like we are taking this output voltage feedback, sorry, this is my reference voltage, this is my reference voltage. So, this is my reference voltage, this is plus, and this is, let us say, my output voltage. So, I am not drawing the complete circuit. Then we have in case of state feedback, we have a PI controller, and this output is going to some, it is like a reference current, and what we are doing, we are directly comparing with inductor current, and that is going to the latch circuit, right. I am not going to discuss because this we have discussed multiple times. So, in traditional current, I would say traditional output feedback, current mode control, this is the way. But in case of state feedback control, we can also add one gain block here. That means, after this IREF is coming in, which is compared with our inductor current. Now we have a current loop gain IL, and that is compared. And again it goes to the latch. So, this current loop gain, it can be already placed because we told that the sense voltage of the inductor current, we have written it is the RS equivalent into IL, right. So, it is coming from the sense resistance. Sometimes we need to intentionally change the gain to do some optimization, right, and that is very much possible in digital control, as well as if we want to change this gain in analog also, although it is difficult, but it is possible. So, in state feedback control, what we did, we have considered this PI controller separately, we have just modeled it, and this is a very well known augmented model, and this reference, as if this is my reference current, is compared with the, I would say there is a gain Kc, and that is my actual inductor current. And if we take tilde perturbation, so this is compared, right, and this is going to the modulator. So, this state feedback control, we are taking both current state and the voltage error, where we have a proportional gain of the voltage controller, we write is a KVP, voltage controller proportional gain. This is like a current voltage controller integral gain, and this is nothing but your current controller proportional gain. Okay. So, we can take this gain, voltage controller integral gain, current controller, voltage controller proportional gain, and the current controller proportional gain that we have discussed, and we can frame it into something like the feedback control, where the duty ratio is generated by their combination. And what is the modulator gain? We know the modulator gain, we have chosen 1 by M1 plus MC into T in case of current mode control, where M1 is the rising slope of the inductor current, MC is the ramps. So, if you do not use a ramp, then it is 1 by M1T rising slope of the inductor current. So, then if we substitute this D expression, so this should be D expression, duty ratio. If you substitute here, then you will get this, and this is my closed loop matrix, and this is my output matrix. So, the closed loop characteristic equation, which is the closed loop matrix, is this, and we can shape this closed loop characteristic impedance by placing the poles, and since it is a third order system, so you will have a polynomial consisting of third order. So, our desired I would say our desired closed loop characteristic equation, our characteristics equation can be written as S plus A1, S plus A2, S plus A3, and this whole thing to be 0. So, we generally tend to prefer real pole, but I will tell what is this. So, in this converter case, we have discussed that this A1, I mean A2 will choose because there are 3 poles. So, one is due to the output capacitor, output cap, one is due to the inductor, and other is due to the PI controller 0, PI controller. So, these are the poles, no poles of the closed loop system. So, for the first case, what we can do? So, what we are going to discuss, one of the pole, let us say this is number 1. So, if I use different color, so this is number 1, this I will place at omega c. That means, I will set A2 equal to omega c, where omega c is the crossover frequency. Why? Because in boost converter and output feedback we have discussed the crossover frequency has to be some fraction of RFP0. So, one pole I am placing which is due to the capacitor is the omega c. The other pole is due to inductor, that is due to the inductor. So, this is 1. Now, talking about the second pole, this should be roughly 10 times omega c, or basically the pole due to 1, that means the pole due to 1 10 times, because inductor should be faster than, inductor dynamics should be faster than capacitor. And the third pole which is corresponding to this is nothing but, if we take Kp plus Kis by S. So, we can write by taking Ki, we can write 1 plus, that means let me write down again. Here if we take the Kp pole, so that means we are talking about Kp plus Ki by S, which is nothing but Kps plus Ki by S. I can write it Ki common into 1 plus S by omega controller Z0 by S. And what is omega controller 0? Because we are taking Ki by Kp, and which I have called here is my A1, this is my here A1. So, if we choose let us say Kp by Ki something, then we can place it. And this case study we have already discussed in lecture number 39. So, lecture 39 already discussed, we have already discussed. So, I am repeating, and generally our crossover frequency should be smaller than RHP0, but here if we choose let us say 0.5, nearly that. So, pole due to the output capacitor is the 10 times faster, and the 0 of the, that means kVi by Kp of the voltage controller. And we have seen this can achieve faster response than output feedback. So, we have seen the state feedback control or state feedback design is faster than our output feedback base. Here it is a state feedback based design, state feedback, or let me erase this part. So, what we discuss, state feedback design approach can achieve well damped as well as faster well damped response even at higher crossover frequency, because that is the problem in output feedback design. So, we can achieve faster, but because of the limitation, and that part we have discussed in this review paper. So, you can check it out that it can respond much faster, that we have already discussed here. Okay. But here still we are using linear control, though state feedback approach is better, but due to linear approach it cannot handle large perturbation. So, performance is limited. So, can we go beyond small signal model? Any benefit using nonlinear or large signal model? So, again we can rewrite the equation, and if we write, suppose the x1 state to be the average inductor current and x2 state to be the average output voltage, then we know that average dynamics x1 dot is this is well known, and x2 dot also, this part we know. So, we are not spending time on this, and here we are writing these are all smooth function, smooth vector function, because there is no discontinuous control input and there is no discontinuity, no discontinuity. No discontinuity. No discontinuity. So, this we can discuss. Now, we can represent this something like x dot equal to fx plus gx into d format, where we can write fx and gx in this format by rearranging. What is the next task? Suppose we create an energy function, kind of energy like function, where half of, if I take the reference I ref to be the reference of the, this is the reference current for average inductor current. That means, we want the inductor current average value to track the reference current, or they should be equal at steady state. Similarly, we want the average value of the output voltage should be equal to the reference voltage, that is our desired, and that is why we have constructed the energy like function. Is like look like half L I square, but this is a error current, and half C V square, and this is a error voltage. Now, if you differentiate this energy like function, because this energy function can be shown to be greater than 0 for as long as this error, that means x1 minus I ref for, if I take this square plus, or I think if x, it can be shown to be for all values of x1 and x2 except for x1 equal to 0, x1 equal to I ref, x1 equal to I ref, and x2 equal to V ref. Except for that point, it is always 0, because it is energy like function. So, if you take the differentiation of this, that means rate of change of energy, we can write dou V dou x into x dot, and x dot is nothing but our fx plus gx into d, and that we have discussed in the previous slide. Now, what is dou V dou x? It is dou V dou x1, dou V dou x2, and what is my dou V dou x1? If I differentiate this function with respect to x1, it will be simply L time this. So, this is nothing but our dou v dou x1, and this one is simply nothing but this one. Okay. So, we obtain this. Then we already know this whole thing is nothing but my dou v dou x. Then what about x dot? It is nothing but this, because it is a 2 cross 1. This is a 2 cross 1 and this is 1 cross 2, right? And this is coming from state space representation, the dynamical equation, correct? This we have already discussed. Next, if we substitute, that means if we simplify this multiplication, after simplification we are getting this x1 minus I ref into this, x2 minus v ref into this. And if we rearrange this function, then we will get this function, this all will be eliminated and we will get this kind of structure. That means this x1, x2 cross terms are gone, x1, x2 is gone, then these cross terms are eliminated. Now, we got this form, that means this kind of form. Now, what is my reference current? In the earlier case, we consider reference current, that means I am talking about a state feedback realization, where we have a reference voltage and this is my output voltage. So, this is my error voltage, okay? Error voltage, this into Kp, okay? And here we have denoted this term to be x1, we have denoted. Then this is added with what? This is added with two things. I mean, one thing is this is a voltage loop gain, this is a Kc, the current loop gain, and that is coming with one is our I ref, which is plus, and another is IL, which is minus. So, in I ref, and this whole thing is my the control current, and that is compared with the sawtooth waveform. So, the I ref can be, because we have discussed in lecture number 18 in state feedback, we have an alternative realization. This can be taken simply our voltage loop integral. So, this is my voltage loop, because so this is something like integral gain into our error voltage dt. This we have considered for small signal based design. So, here we are considering this quantity to be the normalized load current. So, let us say we are considering the normalized load current. So, this is my normalized load current I reference, which is nothing but the normalization factor into the load current, and for a boost converter normalization factor is V ref. So, this normalization factor is carried out in order to achieve the steady state value, average value at steady state should be equal to this I ref, that is my objective. And the average inductor current is equal to V ref by V in times the average load current, that is a boost converter. So, we have considered this. Now, if we substitute this I ref with the normalized load current, then what we will get? We have substituted, we will get this equation V dot x, this equation, and next our control duty ratio is the modulator gain, because I told you that this is our x 1, that is my inductor current, subtraction, this is my I ref, plus there is one more is my x2, which is my output voltage, it is minus reference voltage. Here we have Kp, here we have Kc and they are added up, and that is directly compared with and that is generating my gate signal. I mean, there will be a latch circuit, of course, there will be a latch circuit. So, we will have a latch circuit after that. So, this will go to your, I will say, trailing edge PW, and that will generate the gate sector. So, what is my modulator gain? So, if this is my Vm and this is my 0 voltage, so my modulator gain Fm is nothing but 1 by Vm. But if you take, because if you do not take the RAM, that means the other possibility you can also make it 0. Suppose instead of taking RAM, if you make it 0, because there is no RAM compensation, then this whole quantity will be, this will be 0, it is 0 grounded, or you can simply write this is 0 quantity, it is 0, 0. In that case, our as if the ripple due to this current, the current ripple, that means the current ripple behaves as a sawtooth. So, the modulator gain is nothing but a rising slope of the current, because as if the rising slope of the inductor current will act like a sawtooth waveform. So, this slope is M1 and this we are using for M1 using for the modulator gain. If you substitute, then this expression V dot x will look like this, and what we need for stability, we have to ensure that V dot x is strictly negative if x is not equal to 0, except for origin it should be, that means sorry, if I would say, because it should come to the reference value. So, if x not equal to I ref, x1 and x2 not equal to V ref, that means as long as they come here, it should be negative, it should decrease, and that will ensure the large signal stability. And we will see, when you design state feedback control, we have a constraint in linear LPV model, where we have considered the K factor, that means the crossover frequency, we choose maximum sort of 0.5 times your RHP0. But if we go for large signal based control in state feedback, we can even increase slightly above, so that we can ensure the large signal stability. Under what condition? It will basically, the top switch will collapse, because top switch will turn on and your voltage will collapse and inductor will keep on rising. So, the linear model, the only difficulty, we cannot push further the model validity, but here since we are using a Lyapunov function, we can ensure the large signal stability using this nonlinear model. Another control we can use, because this control we have used a linear state feedback control, that means if you see, the duty ratio is a linear function of state, but your closed loop dynamics is still nonlinear, because your average model is nonlinear, and that way we try to improve the performance. And if you go to linear control, we have linearized using Taylor series. So, the perturb model was valid only for small variation in the perturb quantity around their steady state value, otherwise it is not valid. So, you have a validity issue in the small signal model because of the perturbation size. But if we go to nonlinear control, where we can do exact linearization, there even the perturbation is large, the model still remain valid. But we want to linearize by replacing duty ratio as some function of states in such a way that we can cancel the nonlinearity. So, again if we take the average model that we have discussed, we can write this average quantity in this this is well known, and this just we have discussed now. Now we are redefining the variable. One variable we can take the output voltage, and the other variable we can take the derivative of the output voltage. Then we can take x1 dot x2 dot, we can write it down in terms of, if we take the double derivative of the output voltage, it will be like this, and so this can be represented from this model to this model, where here it is a state space model, where we are writing, it is a second order system, we are writing two first order equations. Here we are writing one second order equation, right? And then since we have redefined that V0 to be Z1 and derivative to be dV0 dt, so that means Z1 dot is Z2, this is straightforward. But what is Z2 dot? It is nothing but the double derivative of the output voltage, and this we have just written, yeah, here, it is here, it is already here. So this quantity will be replaced by my Z2 dot, this quantity will be replaced by Z1, and this quantity will be replaced by Z2, and this is exactly we wrote, okay, after rearrangement. Then we can further write to separate the duty ratio term. That means this quantity, there is no duty ratio, no D, even no V in. So we have separated. Because this term we have to select the duty ratio in such a way that we can eliminate this whole term and replace with another control variable, which will be a linear function of Z1, Z2. Then what we did, Z1 dot equal to Z2, this is the model. So select the control variable D such that this quantity can be replaced by Vm, so that there is no nonlinear function, because there is a product of d square Z1 is a nonlinear term, right? D into Z1, which will come from here, it is also nonlinear. And input voltage in offset we want to eliminate. So we want to make a linear combination. So this, that means this required, if I set this quantity, so this should be Vm by Z1, Z1. Then because we are dividing Z1, so that means this twice D, and then we are making into a square form. Then what we will get, this function that we have to replace, this equal to Z1, and this turns out to be, so this should be Z1. That means if we replace the duty ratio in this way, then my whole term here, it will look like this Vm. So now it is a linear, there is no nonlinearity, and this is another control variable, remember, which should be derived as a function of Z1, Z2, because this represents, even if we take Vm, let us say if we set Vm equal to 0, no other control variable, that means this is the equation where it is a linear equation, but the location of the poles will be decided by the system parameter LC, but that poles may not give sufficient transient performance. That means we want to achieve some desired transient performance, that cannot be met. So this extra variable that we placed in order to create a linear function of Z1, Z2 in such a way the closed loop poles can be placed in a way to achieve faster response. But interestingly, the whole control problem solved to a linear control problem, because we have eliminated the nonlinear control by means of this. So there is no Taylor series linearization, remember there is no duty ratio perturbation limit, but here the duty ratio must be greater than 0 and less than 1. It should not take the extreme values 0 and 1. And where we can make Z1, in fact in more generic term we can take a Vm to be minus K1, What is Z1? Z1 is the output voltage. So, you should take something like Z1 minus the reference voltage, because we need to regulate the output voltage to its desired value. Another one will be, and if we write, okay, just a minute, if we write in terms of, that means if we write Vm, so there is a modulator gain into, here we should write K1 Z1 minus Vref, because Z1 is the output voltage, plus K2 into Z2. Why Z2? Because the derivative output voltage should be 0 at steady state in average sense. And what is the modulator gain? Because as if we are implementing this control logic and there should be a reference voltage. So, since we have replaced that Vm to be what? Vm to be Fm K1 Z1 minus Vref plus K2 into Z2. Okay. So, that means there will be an additional term which will be plus, if you take here, it should be Fm. So, this should be plus Fm by Lc into K1 by into Vref. So, this term, offset term, will also be there along with this. That means this term should come here. Okay. Similarly, we will have another term which will be Fm Lc K1 Vref. But we want to analyze stability for this system. So, this offset term is just as if it is, if there is no offset term, we are trying to get the stabilization at origin, because we want to take any arbitrary initial condition should be driven towards origin, but here we want to drive towards the Vref. So, only adding this offset term will only changes the operating point, but the stability will be determined by this particular term. That means this particular term will decide the stability. So, our stability will be decided by this particular matrix if we solve by suitably, but there is a constraint, because when we take the duty ratio expression, duty ratio has this. So, this will put a limit, and here we have Z1 term, and the limit also the output voltage must be positive, because output voltage cannot be negative. So, it should be positive. Okay. So, in this constraint we need to find the control law. But what is the limitation here? The exact cancellation is not possible, because we have considered only ideal boost converter. Remember, ideal boost converter, but in reality the boost converter is not ideal, and you will get more complex model with including parasitic, and which can create real problem in exact cancellation. That may not be possible. So, practically feasible. That is why most of the feedback linearization comes with something called backstepping, and which will give you some kind of robust performance, because there will be some residual to anticipate residual nonlinearity, because we are relying on the exact cancellation, and that is not possible. If that is not possible, if there is some residual nonlinearity, how to make sure it is stable? That is the first criteria. Secondly, we got a constant on the, which is a limiting factor, and the performance better than LPV model, but not up to the silver limit. Another thing I can say, the nonlinearization, cancelling of the nonlinearity may not be a good idea, rather keeping the nonlinear model and taking the advantage may be the better idea. And this, in order to apply this method comes from the concept of feedback linearization. And this require, if we want to achieve this linearized form, it also need to satisfy something like a similar to controllability criteria, and that require Lie derivative. But we are not going to discuss because this is beyond this course and it is a nonlinear control course. But one thing I can say, we can use a large signal model where we do not need to limit a small duty-ratio perturbation. But even with that, we really face difficulty. Exact cancellation is really difficult, and we still have a limit on the duty-ratio even though the variation is large, but it cannot achieve up to slew rate limit, and it is very sensitive to cancellation as well as the parameter. So then direct switching based control is the better alternative where we can go up to the slew rate limit. That means we can get the fastest response, and that we can use a switching model that we have started with. So that means where we discuss different nonlinear control technique, and one of the case study using Lyapunov function based approach we will take in the next week, in last week in the MATLAB case study, that we want to show that if we incorporate the large signal model with Lyapunov stability criteria, then we can ensure the stability when the duty-ratio variation happen beyond the small signal limit. And then we will show the switching control based approach is the best one to get the fastest response and to get up to the slew rate limit. So with this I summarize that we discuss small signal model, large signal model, we discuss gain scheduling and linear parameter varying model, we also discuss large signal stability using Lyapunov function, and we also discuss exact linearization and nonlinear control using large signal model. So and some of the case study that gain scheduling and then Lyapunov function based approach we will consider in week 12. We will take case studies using MATLAB case studies. So with this I want to finish it here. Thank you very much.